At the heart of every rocket engine lies a marvel of engineering,
7,
the rocket nozzle.
6, 5. We have to go ready to start. 2, 1, 0.
These supersonic nozzles are designed using principles from fluid dynamics and thermodynamics. Unlike subsonic nozzles, which accelerate gases to speeds below the speed of sound, supersonic nozzles propel gases to velocities faster than sound itself. This feat is achieved through a carefully designed converging-diverging shape. In subsonic flow, increasing the area leads to a decrease in velocity and an increase in pressure, while in supersonic flow, increasing the area leads to an increase in velocity and a decrease in pressure. Imagine a rocket engine's combustion chamber, where intense heat and pressure reign. As gases expand from this chamber into the nozzle, a transformation occurs. Through a converging-diverging design, the nozzle accelerates these gases, converting thermal energy into kinetic energy. But why is this expansion crucial? Well, it's all about thrust. To achieve maximum thrust, gases must expand completely to match the ambient pressure. An underexpanded nozzle with a too small exit area fails to achieve this, leading to incomplete expansion within the nozzle itself. On the other hand, an overexpanded nozzle with a too large exit area causes the gas to exit at lower pressure, impacting performance. In this video, I will introduce you to a Jupyter code that helps you to design your own rocket nozzle. You can access the link for this tool in the description below. With this code, you'll be able to generate 3 distinct types of nozzle contours: conical, bell-shaped, and spike. To proceed, you'll require the following input parameters: chamber pressure, ambient pressure, desired thrust, and oxidizer fuel ratio for bipropellant systems. This code uses the RocketCEA library to calculate key parameters of the nozzle, such as expansion ratio, throat area, and exit area. As a result, this code produces graphical representations of the nozzle contour for the different shapes, as well as their dimensions. Besides, the code generates an Excel sheet containing the coordinates of the nozzle contour. The conical nozzle, the oldest and simplest configuration, remains prevalent in many small nozzles due to its ease of fabrication. Sutton notes that a 15-degree half angle has become the unofficial standard for comparing correction factors and lengths across different conical nozzle designs. While larger divergence angles offer shorter, lightweight designs, their performance may suffer. Bell nozzles are more efficient in supersonic gas expansion compared to simple straight cones with similar area ratios and lengths. Their contours can be designed to minimize losses, making them a preferred choice. The length of a bell nozzle is often expressed as a fraction of the length of a reference conical nozzle with a 15-degree half angle. For example, an 80% bell nozzle has a length 20% shorter than a comparable 15-degree cone with the same area ratio. Rao established a method for optimizing thrust by designing the wall contour based on nozzle length, ambient pressure, and flow conditions. This involves the use of isentropic flow assumptions and the method of characteristics to construct the nozzle contour. Angles N and E crucial for this method are obtained according to the expansion ratio. Unlike conventional bell-shaped nozzles, which operate optimally at specific altitudes, spike nozzles offer self-adjusting flow expansion, resulting in improved thrust coefficients. This enhancement is particularly noticeable at altitudes lower than the design altitude. The design methodology for a spike nozzle adopted is rooted in the utilization of the Prandtl-Meyer function, assuming ideal thermal and calorific properties of the gas. At the nozzle exit, the flow is presumed to be parallel to the nozzle axis. This flow is then dispersed across multiple Mach lines, ultimately converging at the corner of the shroud. Each Mach number, between 1 and the exit Mach number, defines a specific Mach line. At the time of recording this video, the code I'm using, which you can find in the description, is in version 1.0.0. The code can be further improved to make it more efficient and accurate. If any errors are identified, they will be corrected. I'm open to any feedback and contributions from those who are interested in collaborating with the development of this code. Soon, I will make a video demonstrating how to use the coordinates generated by the code to design a 3D model of the nozzle in one shape. Thank you for watching. If you've made it this far, please subscribe to the channel for more videos like this and visit my GitHub to explore other similar projects.